Before the lesson begins, I'd like to welcome everyone and thank you for joining me. Today, we are going to learn how to determine the roots of a polynomial function. You'll probably find this lesson a little shorter and more straightforward because the concept itself is not entirely new. We have already learned how to find the roots of quadratic or second degree polynomial functions, and the overall process for higher degree polynomial functions is very similar. The main difference is that instead of factoring only quadratics, we now need to factor polynomial functions of degree 3 or higher. And to do this, we'll apply the factor theorem and the remainder theorem, which provide us with an efficient way to factor higher degree polynomials. By the end of today's lesson, you will be able to solve polynomial equations by using the factoring technique. Now, when solving quadratic equations, we had several methods available. Depending on the question, we could solve by factoring, by completing the square, by using quadratic formula. However, once we move to polynomial equations of degree 3 or higher, there is no general formula similar to quadratic formula that will always produce solutions. As a result, our primary algebraic method for solving these equations is factoring. Of course, we can also estimate solutions by graphing functions using graphing technology, but that will provide approximate values, and our focus will mainly be on using or learning how to solve polynomial equations algebraically by paper and pencil way. Before we begin solving equations, let's review a few important definitions. The points where the graph of a function intersects the x-axis are called the x-intercepts because they intersect the x-axis. The y-coordinate at any point on the x-axis, as you can imagine, is always going to be equal to 0. So this is why the x-intercepts are also known as the point where the function becomes 0 in value. Now, the zeros or the x-intercepts are called the roots of the function. That's a very familiar term for all of us. So therefore, we're going to say that if we say zeros or if we say x-intercepts or if we say roots, we mean the same thing. So how do we solve a polynomial equation? The strategy is actually quite straightforward. So first we need to factor the polynomial completely by using the appropriate factoring technique, so the factor theorem and remainder theorem. And then we have to apply the zero product property by setting each factor equal to 0. Remember that if the product of multiple factors is 0, either one of them can be 0, and then solve the resulting equation to determine all the roots of the polynomial. Now that we have our strategy in place, let's get started with our first example. So what we see here is a third degree polynomial function, and we notice that all terms are listed from highest to lowest degree, and the leading term, the highest degree term, has a coefficient of 1, which means that to factor the polynomial, our focus will be only on the constant term of this polynomial. Now, know that the maximum number of factors that we can obtain here will be 3. That's because degree 3 polynomial. And because the leading coefficient is 1, then every factor, if in linear form, will start with the term x1x. Now, our job is to find out the value of the constant terms in each factor. Remember that based on the factor theorem, these constant terms multiplied together will contribute to creating the constant term in the standard form. So we're going to reverse this relationship now and think, okay, let's use this constant term to figure out what numbers we can have in here. So the possible factors of number 3 are plus or minus 1 and plus or minus 3. So this is a prime number. And for these values of b to be part of each factor, they need to make the polynomial, or they have to give a polynomial a value of 0. So we're going to start with the value of the function at 1. And we're going to say that that would be equal to, I'm just going to set this up and substitute just the value of b. So I'm going to copy this down so that we have it for our next possible value. So here we go. We're going to start with 1 to the power 3 minus 4 times 1 squared plus 2 times 1 plus 3. As you can see here, we're going to get 1 minus 4 plus 2 plus 3, and that will give 5 minus 4, 1, that's 2. So this is different than 0. So therefore, we're going to say x minus positive 1 is not a factor. Next, we're looking into negative 1. So we are finding f of negative 1. So now we have negative 1 power 3, negative 4 times negative 1 squared, 2 times negative 1 plus 3. So when you evaluate this, you get negative 1 minus 4 minus 2 plus 3, which has a value of negative 7 minus 3, negative 4, different than 0. Therefore, we're going to say that x minus negative 1 or x plus 1 is not a factor. So far, we haven't got much luck, but let's check and see what we get next. We have this time the possible value of b equal to positive 3. So it means wherever we see x, we're going to replace it by 3. And what we get this time is 3 to the power 3, 27. Now we have negative 4 times 9. 9 times 4 is 36 negative. And 2 times 3, which is equal to positive 6, and then plus 3. So in this case, then, we're going to say that we have negative 27. Negative 36 plus 6 is negative 30. 27 and 3 makes 30, so that must be 0. So therefore, we're going to say that x minus positive 3 is a factor. So once we discover our first factor, we're almost done, and we're going to start dividing by it. As you divide, you get a quotient of lower degree, which makes it easier for us to factor. And we're going to use coefficients of the given equation here, which are 1, negative 4, positive 2, and then positive 3. And we are dividing here by 3. We're bringing 1 down. And synthetic division works just fine. And then remember, 3 times 1 is going right here, 3. We add negative 1. Multiply negative 1 by 3, that's negative 3. Add again. 2 plus negative 3 is negative 1. Again, same process. 3 times negative 1 is negative 3. We add and we get a remainder of 0, which is what we expect to have at the end here. And we'll say that the factored form would be x minus 3 and then x squared minus x minus 1 equals 0. Now, you're probably wondering that can we try b of negative 3? So if we discover that negative 3 will also help us create a factor, it means that two of the factors will have 3 and negative 3 here, which will make the constant term at least negative 9. So I won't even try the negative 3. But my focus will be on this factor in here, the quotient part of the polynomial division here. And I'm going to think, is it possible to factor it using my good old methods from grade 10? And as you can see, you can't find two numbers that multiply to negative 1 and add to negative 1, at least not integers or even fractions. So we're going to ask for help, the quadratic formula. So we're going to say x minus 3 equals 0, which means x equals 3. That could be one of the roots or one of the solutions. Or we're going to say that x squared minus x minus 1 equals 0. So don't be discouraged. If you see that the factor in quadratic form is not factorable, you can easily use the quadratic formula there. And we have x equals negative 1 plus or minus square root of -1 squared minus 4 times 1 times -1, and then divided by 2 times 1. Just simply use the quadratic formula. And what we get in here is x equals 1 plus or minus. See that you have 1 plus 4, that's 5, root of 5 over 2. So we got two more roots in here, and these two roots are in radical form. So 1 plus root 5 over 2 and 1 minus root 5 over 2. So in total, we got 3 roots. So x1 equals 3, x2 equals 1 plus 5 root of 2, and x3 is equal to 1 minus root 5 divided by 2. I said by 2. Okay, that's a lapsus. All right, so we have another example next. So let's take a look at this. As you can see here, you have a third degree polynomial, and the leading coefficient is different than 1. Now, there are various methods of factoring a polynomial. Sometimes even third degree polynomial functions can be easily factored by using the grouping technique. Remember, you've been introduced to grouping technique in grade 10, and I'm going to take this function and try my grouping technique in here and factor theorem. So let's see how that is going to work. Now, you probably wonder about how did you think of the grouping technique in here, recognizing patterns. So notice how in here you have a common factor of x squared and a common factor of 4. So 4 was very easy to see as a common factor in here because these are fairly small numbers. I can kind of see that we have x minus 3 in a way. So we're going to try that out. So we have 4x to the power of 2, and then here we're left with x minus 3. Now for these two groups of terms, so let me just highlight them so it's easier for us to see where they are. And here we're going to take out -1, and then x minus 3 equals 0. So notice how we end up with with a common binomial. And we will take that common binomial out. So the common binomial x minus 3. And we'll take x minus 3 out. And then in brackets here, we'll have 4x squared minus 1 equals 0. So you can factor the 4x squared minus 1 a little bit more to 2x plus 1 and 2x minus 1. And now we're ready to list all the zeros. So x minus 3 equals 0 when x equals 3. 2x plus 1 is 0 when x equals -½. And 2x minus 1 is 0 when x equals 1/2. And these are our 3 roots. Now, say for example that we couldn't see right away the patterns in factoring by grouping. So the way that you would do this is by using the factor and remainder theorem. So I'm going to rewrite this function one more time. So that's 4x cubed minus 12x squared minus x plus 3 equals 0. So we start off with the constant term in here and then continue with the leading coefficient. So the leading coefficient will give us the possible values of a, which are plus minus 1, plus minus 2, and plus minus 4. The constant term will give us the possible values of b, plus minus 1, and plus minus 3. So we are interested in b over a because we notice that a here is different than 0, which makes us think that our factors will be in the form. So some of them can be x minus b, but we need to have factors of the form ax minus b in this case. So we have to figure out the values of b over a. This is the rational zero theorem. We will derive the values of b over a by simply taking each value of b divided by each respective value of a. So it'll be plus minus 1 over plus minus 1, plus minus 1 over plus minus 2, and then plus minus 1 over plus minus 4. So remember, these are all our b's in here, and these are going to be all our a's in here. And down here, we're going to have more values, so plus minus 3. So we're going to go plus minus 3 over plus minus 1, plus minus 3 over plus minus 2, and then plus minus 3 over plus minus 4. Now, I know that it feels a bit overwhelming because we do see quite a few numbers in here, but remember that once we find our first b over a value, we're very, very close to the solution. Okay, so we can simplify these b over a values into plus minus 1, plus minus half, plus minus a quarter, plus minus 3, plus minus 3 over 2, and plus minus 3 over 4. So we're going to get started with, let's say, plus minus 3, obviously. We all know these answers from the previous method that we used in here, but normally you would try all the b values in order. Use a calculator. You don't have to show the work, but I'm going to show the work for f of 3 here, just so that we can see it. And we'll have 4 times 3 to the power of 3 minus 12 times 3 squared minus positive 3 plus 3. So that will give 9 times 4, 36. And then minus 3 plus, 27 times 4 minus 12 times 3. That will be equal to 0. That you see that 12 has a 4 and a 3, so they can combine to make 3 to the power 3. So right away, even mentally, you can do this. That means that x minus 3 is a factor. So once we discover this, then we start our division. So number 3 is going to sit nicely and quietly here. And now we're going to list our coefficients for negative 12, negative 1, and positive 3. Bring 4 down, multiply by 3, add. And then 0. And then 3 times 0 is 0, add this together, bring negative 1. Negative 1 times 3 is negative 3, and as promised, the remainder is 0. So we're going to say that this will be our x term. This is going to be our x term, and lastly, the negative 1. So x minus 3 is our first factor, and then the next factor would be 4x squared minus 1, because 0x doesn't count. And 4x squared minus 1 will further factor into 2x minus 1 and 2x plus 1. That's the difference of squares. We know how to factor this from grade 10. And from here, we're going to state the roots in a similar way that we did when using the previous method. Now, the next questions are practically remainder factor theorem type of questions, and we are going to look at them in our the next part of the lesson in the next video. As always, thank you for learning with me, and see you next time. Bye for now.